Those must be a lot like further along than this, right?
Yeah, I mean, but if you look at some invertebrate organisms, so without a backbone, there's planaria, these roundworms. So a single worm, if you cut it into 100 little pieces,
Yeah.
each one of the piece will grow a new front end and back end. So they can regenerate their entire body, including their eyes and their brain and everything. So from a 1/100th slice through the middle of the animal, you'll get a new head and tail, including all the right structures regrowing. They'll generate a new brain, an eye in the front, and a new tail in the back. And it's stem cells. It's a rare stem cell within the small piece that's left that do all the regrowing. It's, 1% of all the cells are stem cells, but they're doing all the proliferation in order to build all the front and the back of the animal again.
Wow.
So,
Those work.
yeah, so that sort of gives you a little flavor of some of the powers of stem cells in a regenerating organism, and it really illustrates the self-organization idea, right? Because you're growing a whole new head and eye off one end and a whole new tail off the other end, and they look correct. Those animals are fine.
I feel like worms are less complex. Right. So I
That's
feel like
probably fair. It's probably fair. Yeah.
the amount of information they have to like recreate,
Yeah.
it would seem like that would be less. Like also, I mean, like if you took like 1/100th of a worm and you regrew it, would it like behave the same way that the original worm did?
Apparently they
Oh,
do.
really?
Yeah.
Okay.
Yeah. And they can even, so some of them are hermaphrodites, so they self-fertilize internally, and so they can get back their ability, they can regenerate the sperm and the egg, and they can get back to worms that actually generate new worms. It's fantastic,
That's
actually.
interesting. That's also because their whole body is the same, right? Like their brains is like. I remember maybe this is also like a myth, but I remember you hear when you're younger like that worms have like multiple brains.
And I don't think it's really true. As the planaria grow back front of their head with an eye and the brains, and they get connected correctly, and they grow a nice tail with the gonads, the sperm and the egg in them. And so they seem to be able to do a pretty good job of regrowing. But this has only been shown in invertebrates. You can't do this in animals, with more complicated animals with a backbone. There's a little bit of regeneration you can sometimes get in fish. You can cut off part of their tail and it'll grow back partly. But it's nothing as like these planaria where they can grow essentially their entire body back.
That must mean that they have all that information about their whole body stored at like every point in
Well,
the
no,
body, right?
think about the morphogen gradient. If you got a small little slice of the animal and it still has part of that morphogen gradient that says this is the front end, this is the back end, then they can generate successively. Well, let's go to the next part of the front of the body, and let's go to the next part. And if you just read off the gradient where you are, the morphogen gradient, you say, okay, I know whatever that growth factor is. We know if it's at a low level, we'll make an eye. If it's at a high level, we'll make a tail. And so as long as you can specify, I think people argue that the reason why you can't go more than 1/100th of a planaria is there's not enough space there to establish a gradient now of anterior posterior. But as long as you've got
Okay.
enough to establish a gradient anterior and posterior, then you can regenerate in order things that are at the front versus the back of the animal.
What does it use like when it establishes that gradient? Like, what is it using to like what like information is it using to like establish that?
It's generating a chemical that people call the morphogens,
Oh, that.
and
Oh, that's
they're
what that.
generated
Yeah.
from, say, the back of the brain or the back of the body. And if they're generated from the back, that's the highest concentration will be, and then the gradient will be lower in the front. And if you're going to be a front of the brain cell, then go where there's a low level of the morphogen. If you're going to be the tail, then you go towards where the back is. So they self-organize essentially based
Okay.
on the gradient that's left. But if you get more than 1/100th of the thickness of the worm, then they can't set up a gradient. I went to the International Society for Stem Cell Research 2 weeks ago. It was in Hamburg, and there was a whole session on planaria. I thought it was the best session of the whole meeting. Almost everybody else works on mice or rats or humans, but they had these guys working on worms. It was a fantastic session. So
Were there any like takeaways from that about like crossover research?
Yeah, I guess everybody's trying there's a strong clinical flavor to the meeting. And there's a lot of sort of regeneration companies involved. And certainly people are the most common approach is to take these embryonic stem cells or induced pluripotent cells that can make any tissue in the body and try and direct them to the tissues you want. So it's sort of like a recipe contest, right? Everybody's got their own recipe how to best make blood cells or how to best make muscle cells from a cell that can make any tissue in the body.